The U.S. has more obese people than any other country in the world. Yet most people don't like to be overweight. At any time, an estimated 50 million Americans are dieting. 90% of these diets fail. Why is losing weight so hard? Is it because people only pretend to diet, saying they're eating less, but really they're cheating? In this unit, we'll use statistics to understand dieting better. And we'll discover, through looking at the linear relationship between two variables, that successful weight loss is more difficult than just cutting back. In exploring linear relationships, we'll see that the least squares criterion gives us a specific way to say whether one line describes a relationship better than another. We'll find that the line that is best, according to this criterion, is called the least squares regression line. We'll learn how to obtain the equation of this line from the data points. And we'll learn that we can use the least squares line for prediction, but that we should do so with caution. Renee Kalonsky has been struggling to control her weight for a long time.
I would lose weight, stop, gain it all back, go back to another doctor, do the same thing, take the medications, not take them properly or the way that they were prescribed, and lose the weight again, and then stop, and then just keep snowballing constantly back and forth. At my highest point, I was 253 pounds, and every single time you walk by someone and if a crowd of people start to laugh, you just mentally you feel as if they're laughing at you. So emotionally it was very, very trying, and yet the more upset I would get, the more I would eat.
With the help of an obesity research clinic in Philadelphia, Renee lost 100 pounds. But now, even though she's on an 800-calorie-a-day diet, she's having trouble losing more.
So it looked like when I saw the scale, you'd lost about 1.5 pounds this week?
Right, but it's still the same frustration. I'm still cutting down less and less and not losing. It seems as if it's always the problem of not losing.
Here's the problem that dieters like Renee face. In the beginning, as she reduced her caloric intake, her weight went down also. But eventually, even as she continued to reduce her caloric intake, her weight leveled off. She essentially stopped losing weight. Researchers in Philadelphia designed a study to try to understand why people like Renee stop losing weight. They isolated two factors they wanted to track. First, metabolism, the number of calories you burn each day. Metabolism, or resting metabolic rate, is measured as the amount of oxygen consumed in a 24-hour period. The second factor is lean body weight, all of the weight in the body which is not fat. Lean body weight is the part of the body that actively burns calories, whereas fat stores energy. Weighing subjects underwater helps distinguish lean body weight, which sinks, from fat, which floats. At the beginning of the study, each subject was measured for metabolism and then for lean body weight. Subjects continued to be measured as they lost weight. Now, overall body weight is comprised of both lean body weight and fat, and as people lost weight, they lost both. But at some point, lean body weight loss slowed or even stopped. Here is a scatter plot of simplified data for 12 people at the beginning of the study. Researchers believe that changes in lean body weight might explain changes in metabolism, so it is the explanatory variable, which goes on the horizontal or x-axis. The response variable, resting metabolic rate, goes on the vertical or y-axis. There's a clear positive association between the variables. As x goes up, y goes up along with it. And the pattern of the relationship is roughly linear, that is, the points fall roughly along a line. In a case like this, we often want to fit a line to the data, to summarize the relationship, and to enable us to make predictions. But just how do we fit the line? There are a number of different possibilities. Which line is the best one? We want a line that falls as close as possible to the points. Because we want to predict the response variable y, a good line is close to the points in the y, or vertical direction. So we want to make the vertical distances between the points and the line as small as possible. A reasonable line will pass above some points and below others, like this. To make this more vivid, we'll use a graph with just 3 points. As we move the line about, some of the vertical deviations get larger and some get smaller. We can't make them all small at once. How can we measure how much the line misses the points? Let's first measure from the points to the line in the vertical direction. We find that some of the deviations are positive and some are negative. But if we square the vertical deviations, the squares are all positive. Add up the squared deviations. The bigger the sum, the more the line misses the points. So we want the line that makes the sum of the squares of the vertical deviations as small as possible. If a line does this, it satisfies the least squares criterion. We call this line the least squares regression line. Now that we have a basic understanding of the least squares regression line, we can use it to make predictions. This is the least squares regression line for the diet study. It is the best line for predicting y, in our case metabolic rate, from x, in our case lean body weight. So knowing someone's lean body weight, we should be able to predict, using the line we found, what her metabolic rate will be. Let's try it for one of the subjects in the study. Before dieting, this person's lean body weight was about 42 kilograms, and her metabolic rate was about 1,200. After dieting, she lost about 9 kilograms in lean weight. Now, based on the line we've come up with, we would expect her metabolic rate to drop to around 990. But in fact, it dropped lower, to 913. If this were just an isolated case, we could attribute this decline to natural variation. But in almost every case, metabolic rate drops slightly below what was predicted by the original regression line. This unexpected result led doctors to a new understanding of why dieting is so difficult.
If you cut back on your food, or if you're starved, one of the adaptive changes that is bred in, that has allowed us to survive eons of famine, is that we're able to burn less and less and less the more we starve. This allows you to survive about 3 times longer than you would otherwise if you weren't able to lower your metabolic rate. What's new is that it turns out that each time you're exposed to famine, or each time you diet, you get better at lowering your metabolic rate, which means that each time you diet, you tend to lose more slowly, and when you go off the diet, you tend to gain back more quickly.
This change in metabolic rate helps explain why dieters can't seem to lose that extra weight.
And it needn't have to do with just not being able to adhere to a diet or not having the willpower to discipline food intake, but it indicates that there are actually mechanisms that the body employs which are fighting, trying to compensate for the changes that you're trying to impose. But on the other hand, it does not mean that the situation is hopeless. The amount of decline is relatively small, and it's not one that can't be overcome.
This information can be helpful to dieters like Renee. By understanding how her body's metabolism is working against her dieting success, she's able to accept the limits of her weight loss program.
I know that where I am now is probably where I'm going to have to be satisfied at being. I know that now I have done the best that I can, and I just can't seem to go any further than what I have. But however, I can maintain what I have, which is something I've never done before.
We now know that the least squares regression line is the one that fits as close as possible to the data. But how do we find this line? Well, it's a mathematical problem with a fairly straightforward solution. The equation of any straight line has the form y equals m times the given x plus b. In this case, the line gives a predicted value of y, so we'll call it y hat, to emphasize that it's a prediction. Now, finding the line by hand is a bit tiresome, but it's worth going through the steps so that you'll understand where the line comes from. M, as usual, is the slope of the line. Since our object is to find the line with a slope that minimizes the vertical distance of all the points on the graph, we need to use all of the points to calculate M. This is the formula. It looks complex, but it's made up of only 3 quantities: n, the number of observations, the x value of each observation, and the y value of each observation. The Greek sigmas just mean to add up these values for all of the observations. We have everything we need to know to solve this equation. The easiest thing to do is to plug in the number of subjects. For the rest, we need a table of the values of x and y for the subjects in the study. We add up the x values and put this here and here. We do the same thing for the y values. Here we put the sum of all the squared values of x. Finally, we put the sum of the products of all the x and y pairs here. When we do the arithmetic, we come up with a slope of the line of 24.03. We also need to find b, the y-intercept. To find it, we use another easier equation. Y bar is the mean of the Y values for each observation. So all we need to do is divide the sum of the Y values, which we already have, by 12 and put it here. We do the same thing with the X values. We already know M. Doing the arithmetic, we get B equals 201.88. Now we've found the equation for the least squares line for these data. It's y hat equals 24.03x plus 201.88. It's easy to draw the line once you know the equation. Just pick two convenient x values, plug them into the equation, and find the corresponding y values. Then plot these points and draw the line through them. Now you can calculate the least squares line. Fortunately, many calculators have the recipe already programmed so that you only have to enter the x's and the y's. But the point is not simply to plug numbers into an equation or follow a rote recipe. The point is to understand the least squares idea and to apply it where appropriate. Using the rote approach, we can fit a least squares line to any set of data. For example, here's data on corn drying, an issue vital to farmers. X is the number of minutes the dryer runs, and Y is a measure of the moisture of the corn. There's a negative association, but the pattern in the data is curved, not linear. The least squares line shown here is perfectly correct mathematically. It's just that it's the wrong pattern for these data. It doesn't make sense to fit a line to a nonlinear pattern. Even when the scatter plot does show a linear pattern, a prediction from the least squares line may be nonsense if the x in question lies outside the range of the data used to fit the line. Here's a plot of one woman's wages over 3 years. 2 years ago, she took a part-time job at a fast food place and earned $6,000. Last year, she worked full-time for $11,000. And this year, she got a promotion to manager and earned $23,000. The regression line for these points looks like this. Now, with this line and its equation, we could predict that if the woman stays on her job for 7 more years, she'll be making about $67,000 a year. The problem with this prediction is that it extrapolates far beyond the existing data. It assumes that the linear pattern just continues. As much as we might wish it were so, wages do not often increase linearly for very long. Remember, when we look at a graph, we look first for an overall pattern and then for points that lie outside the pattern. The overall relationship between x and y in this scatter plot is roughly linear. There's also one observation that stands out from the rest, this point here. If this point weren't here, the least squares regression line would look like this. It is quite a distance above the extreme point. When we add this one point, it pulls the least squares line down to here. The least squares line always makes the sum of the squares of the vertical distances as small as possible, so it can't afford to miss this isolated point by very much. A single point that is away from the others in the x direction has a strong influence on the least squares line. If you see a point like this, be sure it's correct, and beware of its strong influence. In this unit, we learned the recipe for calculating the least squares regression line. It's a common statistical tool because predicting a response variable y from an explanatory variable x is a common problem. We also learned that before using this recipe, you should think about whether a line is really the appropriate pattern in the data. Extrapolate only with caution. And watch out for extreme observations that heavily influence your calculation.